We finished Chapter 7 by looking at testing claims about standard deviation or the variance. There are two requirements. First, that it is a simple random sample, and the population has a normal distribution. And note, this is a fairly strict requirement. It does not have the exception that, for instance, n is greater than 30. Because we're doing variance or standard deviation, the test statistic is the chi-square, and we've got to use Table 6. Properties of the chi-square distribution: remember, all the values for chi-square are non-negative, and the distribution is not symmetric. Each critical value of chi-squared in the table corresponds to an area given in the top row. That is the cumulative area to the right, not to the left, as was Table 4 for the normal distribution. So, a critical value with alpha equal to 0.05, you would use the areas of 0.975 for the chi-squared left and 0.025 for the chi-squared right. Please note that we took the 0.05, we cut it in half to 0.025. That gave us the one to the right, and then 1 minus the 0.025 gave us the 0.975. Okay, now our methods are just like they were before. It's the same steps. Really, the only difference is that we are using a different test statistic, because now, of course, we're doing the standard deviation or variance. So, symbolic form of the claim. Symbolic form for the claim is false. H1 does not contain the equal sign. H0 does. Select alpha. Usually they give us the alpha. Identify relevant statistic and determine the sampling distribution. Find the test statistic, the critical values, and the critical region. So this is for the critical value method. Reject H0 if the test statistic is in the critical region, or fail to reject H0, the null hypothesis, if the test statistic is not, and then restate the result in simple terms. P-value method, very similar, except now we're going to compare the p-value to alpha. And again, the difference between critical value and p-value methods are that the p-value compares an area to alpha, another area, whereas the critical value here will compare two chi-square scores that would bound those areas. And then we finally have the confidence interval method. For two tails, construct a CI with a confidence level of 1 minus 2 alpha. Use Table 6 again to find the two values. Reject the claim if the parameter is not included in the CI. Again, these are the same steps that we've used now for mean and proportion. The only difference is we have a different test statistic that's involved. So let's look at an example. We are going to look at the sample heights for 10 supermodels. They have a mean of 69.825 inches and a standard deviation equal to 0.800 inches. Research from other sources says the population standard deviation for women's heights is 2.6 inches. Use these results to test the claim that supermodels have heights with a standard deviation that is less than 2.6 inches for the population of women. Use a 0.01 significance level. And again, just as in earlier sections, what we're doing is using one sample to test a claim for the entire population. So, are the minimum requirements met? It is a simple random sample. There are no outliers. So, first we're going to start off with the critical value method. Our sigma is less than 2.6 inches. The counterclaim greater than or equal to 2.6 inches. Our H0, sigma equals 2.6 inches. H1, it is less than. That goes back to our claim, less than 2.6 inches. Alpha is 0.01. And again, we're going to use the chi-square distribution. So, for sigma 2.6 inches, we have n is 10. That's the number in the sample. S is 0.8. So chi-squared will be n minus 1, s squared. That's the sample variance over the population variance. 10 minus 1 times the 0.8 squared divided by the 2.6 squared. That gives us 0.852. Using degrees of freedom of 9 and the area 0.99 to the right, because remember we are using 0.01 as our alpha, and so 1 minus 0.01 will be 0.99 to give us the area to the right, because we are using the 1 for the less than case. So chi-squared in that case would be 2.088. Now, we've got this one from the test statistic, and then we've got this one from using the table based on our alpha. Since the chi-squared equals 0.852 is less than the chi-squared equals 2.088, we reject the null hypothesis. So note that this 0.852 is more extreme than the 2.088. It's more to the left, more extreme, and that's why we reject the null hypothesis. And then we restate, there is sufficient evidence to support the claim supermodels have less variation in height than women in general. Alright, now we're going to look at the confidence interval method. So for a left-tailed test, sigma is less than 2.1 inches, so that's why it's left-tailed. And alpha is still a 0.01. The confidence level is 98% because it's 1 minus 2 alpha. 2 times 0.01 would be 0.02. 1 minus 0.02 would be 98% or 0.98. Again, degrees of freedom is 9. Areas are 0.01 and 0.99. So chi-squared to the left, 2.088. Chi-squared to the right, 21.666. And again, if you get confused, like, which one's which, and you're not sure in the equation, just remember that on this side, because we've got this less than that, less than this, you want the bigger denominator so that this whole thing will be smaller, because the numerator parts are the same on both sides. So 0.9 times 0.08 squared divided by the 21.66, and I should point out this is chi-squared L and chi-squared R. They're already squared, so don't square them again in the denominator. Whereas here we just had S as 0.8, so you did have to square that one. So plugging in our numbers, we end up with the sigma squared is 2.266 up to 2.758, and then if we square root all three of them, we get sigma is between 0.516 and 1.661. Please note the entire interval is less than the null hypothesis. The null hypothesis would be that it's 2.6 inches. The entire interval is less than that, or another way of putting it, the 2.6 is greater than all of that. So we have to, again, reject the null hypothesis. Therefore, there is sufficient evidence to support the claim supermodels have less variation in height than women in general. So it should be pretty clear by this time that really, whether it's mean, proportion, standard deviation, and variance, we're doing the same thing each time. What's really changing is what is our test statistic, and therefore what table do we use. And then secondly, for any of the methods, we could be doing a critical value method, a p-value method, or the confidence interval method. And so that ends section 5.